Um, I'm happy to welcome Henry Adams from Colorado State University, and they'll be speaking on bridging applied and geometric topology. And the floor is yours.
Welcome. Thank you, Daniel. And I'd like to thank all of the organizers. It's been a really fun conference, so thanks for sticking with it till the end. In the chat right now, I put a link to the paper I'll be talking about and the slides. This is joint work with Baris Coskunuzer, who I see just joined. And Baris is really a geometric topologist, whereas I am not. I'm more of an applied topologist. And I really learned a lot from Baris over the last year working on this project together, as I'll explain. It's been fun to see more and more interactions between applied topology and geometric topology. We had the series by Peter Bubenik this week. You know, some other talks, maybe you saw talks by Atish Mitra, Vitaly Kurlin, Tom Needham, Ximena Fernandez, Ryan Grady, that we're talking about persistent homology. And I think there's room to continue to find interactions here. I'll be speaking on a particular paper, geometric approaches on persistent homology, just this last year. So let me say, if you're interested in learning more about applied topology, one way to do so is AATRN, which stands for Applied Algebraic Topology Research Network, which actually Peter Bubenik helped start, and now I help run with Sarah Kalishnik and Alkanon Solomon. But we have an online seminar that's been going on for 5 or 6 years or so, but because of the pandemic, we really increased our activity, and we host interview series and tea times. So we have a YouTube channel with over 2,000 subscribers, over 300 videos now, and about 20 hours watched per day, which is surprising to me, this specific area of topology. All right, so I do a lot of research on Vietoris-Rips complexes, which are used in geometric group theory, but let me describe them a little bit. So if X is a metric space and R is a scale parameter, then a Vietoris-Rips complex is a way to thicken that metric space according to the scale parameter R. So every point in your metric space is a vertex in your simplicial complex, and you add in a simplex into the simplicial complex when the diameter of that simplex is at most R. So the diameter of a simplex is just the length of the longest edge. So on the left, I have a metric space with approximately 10 points, and my scale parameter is perhaps 1 inch. And so I add edges between any two vertices that are at most 1 inch apart. And these simplicial complexes are called flag or click simplicial complexes, because whenever you have 3 edges forming a triangle, you automatically glue in the 2 simplex. And whenever you have all of the edges of a simplex, you automatically throw in that simplex. These spaces get a little bit crazy when you build them on top of infinite metric spaces, right? So if you build this on top of the circle, you have a vertex for every single point in the circle. And so as soon as R is positive, you have an infinite dimensional simplicial complex. But they still have nice properties. If you build a Vietoris-Rips complex on top of a manifold, then for small scales, you recover the homotopy type of the manifold, even though it's an infinite dimensional simplicial complex. And we know, for example, the Rips simplicial complexes of the circle, you get the homotopy type of a circle for a while, and then these equilateral triangles appear. And at that point, you actually get the 3-sphere. And after that, you get the 5-sphere, 7-sphere, 9-sphere for shorter and shorter windows of scale parameter, until finally you reach the diameter of the circle, and the Rips complex is contractible. So some history: they were invented by Vietoris to define a cohomology theory for metric spaces, right? We already had a cohomology theory for simplicial complexes, so associate simplicial complexes to metric spaces and take the limit for Vietoris as R goes to 0. Rips use them in geometric group theory The Vietoris-Rips complex of a delta hyperbolic group is contractible as long as the scale is bigger than 4 times delta. And so, here you're looking at the scale parameter going to infinity. Applied topologists instead look at intermediate scales. You want to recover the shape of a data set, this data set in purple here. So you build a Vietoris-Rips simplicial complex on top of it, and you can recover homology groups or even homotopy types in certain situations. So I won't say too much background on persistent homology, except that these persistent homology bars encode lifetimes of features. So in this 2-hole torus here, we have 4 one-dimensional holes, and the bars encode the lengths of scales for which they persist when you build, say, a Rips complex on top of this and increase the scale. And if you have a nearby data set in purple, the barcodes that you get out are also going to be nearby, recovering the 4 holes. Any background questions before I go on? All right, so in this project or paper or talk, we'll be looking at specific metric spaces. Our metric space is going to be the vertex set of a finite graph equipped with the shortest path metric. So in the graph, adjacent vertices are at distance 1. And then when we build the Rips complex and we increase the scale, at scale 2, we're going to add in edges whenever vertices are connected by a path of length at most 2. And then in the Rips complex at scale 3, we're going to add in edges whenever the vertices are connected by a path of length at most 3 in the original graph. And once you know the edges that appear, you just create the clique complex. You throw in all possible simplices on top of this. So graphs are one-dimensional, but when you build the Vietoris-Rips complex on top of a graph, you can certainly get 2-dimensional holes, right? Like if your graph is this mesh surrounding a tetrahedron or a sphere. You can also get higher dimensional holes, even if you might think they shouldn't appear. So start with a graph which is just 6 edges forming a loop. When you build the Rips complex at scale 2, you add in all of these triangles, 6 triangles sort of around the outside, forming a cylinder. But you also add in this triangle and this triangle, which cap off the top and bottom of the cylinder to give you a 2-sphere. So even when you have one-dimensional features in your graph, you might think you don't get higher dimensional homology, but you can. Here you'll get 2-dimensional homology at this scale. I should say that any simplicial complex can be realized as the Vietoris-Rips complex of some graph. That's just because, and this is up to homeomorphism. Just take the barycentric subdivision of your simplicial complex, and now you have a clique complex. So it's the Rips complex of the underlying graph of that barycentric subdivision at scale parameter 1. So in this project with Baris, we look at lifetimes of persistent homology features. So the birth time is the small scale when it first appears, and then the death time is the scale R in the Vietoris-Rips complex such that it fills in or becomes homologous to an earlier cycle. And so we can bound the length of bars using ideas from geometric topology that Baris has taught me and really introduced to applied topology. So our first theorem uses thick-thin decompositions. And we prove that if you have a 2-dimensional homology class, sigma, then the length of the corresponding bar, namely the death time minus the birth time, is at most the square root of the area of the homology class plus 1. And the area of the homology class is just the number of triangles in the minimal area generator for that homology class. Our next theorem works with homology of any dimension. So the persistence of a k-dimensional homology class is at most the width of that homology class plus 1. Let me just define the width for you. So again, you look over the minimal width generator in the entire homology class. The width that we look at is using sweepouts, which are distance to a vertex. So take a vertex in that chosen generator for your homology class, and then look at the distance to that vertex. So you have these different level sets, okay? And the width of a particular sweep out is just going to be the maximal diameter curve here in red, which might be multiple components. So it's like you have a homology class, you can minimize over any generator, and then any generator you choose, you can minimize over any vertex, get these sweep outs, and the width is this min-max, minimum over all homology generators, all sweep outs, distance to a vertex, but then you look at the maximum diameter of one of those level sets. So for example, if our homology class is this egg, right, then the best sweep out would be the red sweep out, which has smaller width than the blue sweep out. Theorem 2 is, as far as I know, maybe better than Theorem 1 in at least 2 respects. One respect is it's for k-dimensional homology as opposed to 2-dimensional homology. And the second reason why I think it might be better is because of this example using a thin long box and a tetrahedron. In these 2-dimensional homology classes, the thin long box will disappear soon after it forms, right? At a small scale, this box will form, but soon later, each of these circles will become contractible when we increase the scale, and the thin long box is going to fill in. So that's showing that the area bound is not very good for this thin long box. The area bound can be quite large. Area can be large. The persistence of this box will be very small. Whereas in Theorem 2, the width of this thin long box is going to be 4, right? It's going to be quite small. So you can get sharper bounds in examples like this. We conjecture that you could prove versions of Theorem 1 where you, of course, replace area with k-dimensional volume, and perhaps you want a kth root here instead of a square root, but I don't know that for sure. It'd be interesting to search for lower bounds, potentially using things like width or codimension 2 width or codimension 3 width instead of codimension 1 width. So a lower bound would say, can you look at the geometry of a generating homology class and say, based on this geometry, I can say that the corresponding persistence bar must last at least yay long. And again, we're working with quite discrete metric spaces here, vertex sets of graphs where all of the edges have length 1. Sort of an easy context in which to get started, although we had to put in some work to define things like width or thick-thin decompositions in that context. But you'd like to generalize some of these ideas to much broader classes of metric spaces. All right, so in my remaining 5 minutes, I think I'll give the proof of Theorem 2, say a couple words on the proof of Theorem 1, and then point out some more general questions. The proof of Theorem 2 you can sort of summarize as follows. So here we have some homology class, and I've drawn here its generator. We find a nice sweep out where all of these curves have bounded diameter. And then we want to show that the persistence is at most the width plus 1. So on the left, we're sort of looking at the scale parameter, which is when this class was born. And then we're moving forward in scale. And on the right, we're looking at a larger scale where this class is now filled in. We need to prove that this becomes null homologous. And the way we do this is we take this K-cycle, and we break it up into slabs, slabs connecting adjacent slices. Okay. Now, the increase in scale parameter is such that we've exceeded the diameter of any slice. So any slice just fills in with a lot of simplicities. And furthermore, this +1 allows us to sort of bound the diameter of the slab connecting two slices. So we've taken this K-cycle here and we've chopped it up into a sum of K-cycles. And each such K-cycle is filled in by simplicities because the scale is larger than the diameter. That's the general idea here. Theorem 1 was doing this two-dimensional version, bounding by area. I like the ideas here just because they involve thick-thin decompositions. Roughly speaking, we decomposed our homology generator, which is a singular two-surface, into the thick parts and the thin parts. The thin parts fill in much as before. Okay, you can sort of cut them into slices. And on the thick parts, we use an isoperimetric inequality to show that the thick parts also fill in once you increase the scale by this amount, depending on the area. So thin parts are easy to fill in. Thick parts, they fill in depending on the area. I'll say the reason why the area bound comes in is because pick a vertex in the thick part. Because it's thick, that means that the ball around that vertex is embedded, okay? And we can use an isometric inequality to say you have to have at least so many vertices in this ball. And then because the area of this generator is small enough, you can show that two balls cover this entire thick part. And then once it's covered by these two balls, we've bounded this distance, and we can really fill in this loop at the intersection of the balls, and then fill this in by a bunch of tetrahedra, where each tetrahedron looks something like this. Okay, so we have a loop's worth of tetrahedron filling in this thick part. So in summary, we give some connections between lifetimes of persistent homology classes and Vietorships complexes based on ideas from geometric topology, including thick-thin decompositions and sweepouts. But there's more work to be done, lower bounds, and getting analogous results for broader classes of metric spaces besides vertex sets of graphs. I'll use my last 2 minutes just to throw out some emerging connections between applied topology and Vietorships complexes and other areas of pure mathematics, topology, and geometry that you might find exciting, and I'd be happy to talk more about. Myself and others are quite interested in Vietorships complexes of spheres. So I mentioned how when you take Vietorships complexes of the circle, you get the homotopy types of the circle, the 3-sphere, the 5-sphere, the 7-sphere. It's really unknown what happens for higher dimensional spheres. We know the first new homology type that appears, but beyond that, we really don't know. Lots of good connections to polytopes here. There should be nice Morse and Morse spot theories. So Matsuremski has produced, he's proven good results using Besvina-Brady Morse theory. I mentioned Morse spot theories because in symmetric spaces like the circle or the spheres, when you get a new critical simplex that appears, you really have maybe a continuous parameter space worth of critical simplices that all appear at the same time. Tokunda Momoli and Sunghyuk Lim and Osman Okutan have recently connected Vietorships complexes to Gromov's filling radius in a really tight sense, and they give bounds on lengths of persistent homology intervals. If your metric space is discrete, the Vietorships complex is a nice topology, but if your metric space is something like a manifold, the Vietoris-Rips simplicial complex really has the wrong topology, and the right topology is produced by using Wasserstein distances. So there's relationships now with optimal transport. Let me plug this question for geometric group theorists. Take the integer lattice, equip it with the taxicab metric that Greg was just talking about, or sorry, Kurt was just talking about. The integer lattice with the taxicab metric should be contractible when you take the Rips complex as soon as your scale parameter exceeds the dimension, right? So, and when you're in 2D, you have all these squares, and as soon as you reach scale parameter 2, all these squares fill in with tetrahedra, I suppose. But we don't know yet a proof that these spaces are contractible once you exceed n. And Matt Zaremski and I and others have chatted about this, but nobody knows how to do it. And maybe the last thing I'll say is that there's recent connections to Borsuk-Ulam or waste of sphere theorem. So the Borsuk-Ulam theorem is when you map the n sphere to n-dimensional space. Gromov and others have studied waste of sphere theorems when you map to lower dimensional space. And we've recently understood some versions of Borsuk-Ulam where you instead map to higher dimensional space using Rips complexes. So certainly antipodal points don't need to collide when you map to higher dimensional space, but you can show that the convex hull of a set of bounded diameter intersects with its antipode. All right, so I'll end there. Thank you so much for your time and attention. And given that we're at the very end of the conference, we should also thank all of the organizers and all of the speakers throughout these last 3 days. So thank you.
Let's thank our speaker and let's thank the organizers. Are there any questions for Henry?